Hi, and welcome back. Okay, so we're going to pick up where we left off, and I'm going to show you how to code up some Matlab. Hopefully, you're already familiar a little bit with Matlab and how it works. So this will just be a review of that. All right. So in this module, we're going to go over the numeric code for the irrotational flow over a forward-facing step. This is the one I did in the previous lecture. And really, this means I'm going to introduce you to this psi.m file that I wrote. And you can find that M file on the course website. And I'm going to go over the code. I'm going to go over how I set up the initial conditions, iterating to a solution, and eventually then writing those .dat files. All right. This is, just to remind you, this image right here is the one that I showed you in a previous module. And so I want you to just recall that because we're going to use that when we discretize. All right, so here's the terminal window. And you can see where we're at here. I got this psi and plot script files. The two of them are together. And this tilde just means that that's the backup for it. So Linux automatically makes a backup for you every time you open and close a file. Those are there. So let's open this. And I'm going to use something called VI. And VI is a really old editor, like older than Notepad and those sort of things. But it's a non-GUI editor. So I love non-GUI stuff. In other words, it won't work with your mouse. But basically, it will work over a terminal that you're logged into another computer, and that's important to me. So if you just type VI, maybe I should use editor. All right. And where's the home page for it? Let's see here. There we are. So VIM is the improved VI. And so you can go to this this web page here, and you can download this and put it on your computer. It's open source. So this is the VI web page, or VIM, as this tool here has written on it. All right. So that's VI. So I'm going to say VI, psi.m. And that's going to open it. So you can see it kind of looks like any regular editor. Now it feels a little clunky when you first start to use it. That is for sure. So if you're not familiar with it, beware. So in order to edit it, I have to type I. And when I did type I, you can see that it created this insert. And in order to get out of the edit mode, I hit escape, and that gets me out. And then I hit colon, and it brings me to this command line, and I can do something like write the file in the command line, or I can quit the file. And if you get into a lot of trouble, you just hit escape a bunch of times, and then you hit colon and hit quit exclamation point, and that means I'm really serious. I want you to quit this. And it will quit without writing, so be careful with that if you're trying to save your edits. Okay, the rest of it, if you really want to learn VI, I would recommend looking at some YouTube videos or reading the web page a bit, because I just don't have time here to go over VI. But this is the code, right? And so let's go over this code line by line with this image in our mind. So what happens in this code is this pound sign here means it's a comment, right? So it ignores everything past the pound sign. So the first thing it does is it sets the variable iStep. And iStep is the number of iterations we're going to take. So remember, we have this domain. We have this domain right here. And we're going to march through this domain. So I'm going to use that central difference stencil that we had talked about here. And we're going to calculate the value of psi using its neighbor values. And we're going to march through the domain, recalculating all of the psi's within the center of the domain, basically generating a solution. And but before we do that, we have to impose the boundary values of psi. So on this slide, I have the boundary values of psi imposed. So the first thing I do is set the number of iterations, and that's the number of times I'm going to go through and sweep through or march through the mesh. And that variable is not being used yet, but I'll show you where it comes in. Now I get into this nested loop. So this is a nested for loop right here. You can see I'm marching through I and I'm marching through J. This domain here is 10 in the I direction and 6 in the J direction. So I march through for I is equal 1 to 10 and for J is equal 1 to 6, and I set the value of psi, and I'm calling the variable S here. I set it everywhere equal to -1 initially. So I'm initializing the whole domain to -1. And I like -1 because I know it's not the right answer. And so if I have any kind of mistake, it's easy to spot that if I see a streamline of -1. Now the ends close this first end for closes this loop, and the second one closes this loop. So I'm done with that nested loop. And then I come into this section where I'm going to set all the boundary conditions. So I have to comment this out when I write a note to myself, like set boundary conditions. So the first one I'm going to do is along the floor. And so along the floor is this bit right here, right? From 1 to 6. So J is going from 1 to 6 while J is set to 1 and I is going from 1 to 6. And then I is set to 6 while J goes from 1 to 3. And then J stays 3 while I goes 6, 7, 8, 9, 10. And we're going to set the value to psi equal to 0 along that step. So here's what we're doing. We're going from I is equal 1 to 6 and J is equal to 1, and I'm setting the value of psi equal to 0. So I'm overwriting what I did right here. And I find it slightly annoying that Matlab does not let me use 0 for an index. So that means that our lowest value of J is 1 instead of 0, which I find slightly annoying. But that's just what we have to live with. So J of 1, the index is 1, represents the floor. Now I'm going to crawl up the side, the side of the step, up the step here. So I is going to be set to 6 while I march J 2 and 3, and I set the value at x equal, or I equals 6, J equals 2, I equals 6, J equals 3, both to 0. So that's this little loop right here. And now I got to go along the top of the step up here. So J is going to be equal to 3, and I is going to go 6, 7, 8, 9, 10. So that's what we're doing here. I is going 6, 7, 8, 9, 10, while J is equal to 3, and I set psi equal to 0. And so I think that makes sense, right? Here's along the top, and along the top of the ceiling, J is equal to 6, and I just goes 1 to 10, and I set the value of psi along the top equal to 5. So 0 to 5 is the difference here in the inlet, right? So that really specifies what the volume flow rate is into our domain. Now, the inlet itself, we decided that we're going to go psi is equal to 0, 1, 2, 3, 4, 5, and along the inlet. So I'll just march along here. I'll go, you can do this more than one way, but I'll let J go from 2 to 6, because I've already set J equals to 1, right? And then I'll have X equal to 1, and I'll just have J go, then J minus 1 will go 0, 1, 2, 3, 4, 5, 6, or in this case, since it starts at J equal 2, it'll go 1, 2, 3, 4, 5. Okay, so that does that. Now on the back side, we have to specify that all of the flow that comes in here has got to be squished into the back side of the domain. That means the difference in the stream function from the inlet across the inlet has to be equal to the difference in the back, so that the same amount of flow that goes in, volumetric flow, goes out, right? And so that means I need psi at the top of the step to be 0, which I've already set, and then it needs to march in such a way that at the top of the domain, psi is equal to 5. So the way to do that is just kind of this little algebraic equation here that I wrote. I'm going to set the value of I equal to 10, and the value of J is going to go 3, 4, 5, 6. And you can see this little expression will do exactly what I want it to do. When j is equal to 3, j minus 3 will be 0. And so 0 times whatever is 0. So that'll set the value of the string function there to be 0. And then it'll march on up. And when j gets to be 6, which is the top of the domain, 6 minus 3 is 3. 3 times 5 divided by 3 is 5. So I'm going to end up with my 5 at the top there. So that's great. That's exactly what I wanted it to do. Okay, so that just set the initial conditions. And now what we're going to need to do is, I'd like to first write the initial conditions to file so that I can see them. And then next I would like to go ahead and start the domain marching. So this little command right here is kind of nice. This right here, what I'm doing right here is I'm building the file names for the data dumps. So I want to call the files psi, and then I want there to be 6, I want there to be, I'm going to hit undo here. That's U. That undoes whatever I just typed. There'll be 6 digits that represent the iteration number, right? And so it'll be 6 digits and that are iteration number. And the reason I'm doing this 0 padding here, that's what this does, so that the files won't be called psi1, psi2, psi3, psi4, psi5 up to 10, and then it'll go psi 10, 11, 12. I don't like that because if you've ever done a listing, you'll see that it won't necessarily list them in order. So what I want to do is 0 pad. So I'll have psi5, sorry, the first iteration, the first dump will be psi1, but there'll be 5 digits, 5 zeros in front of it. And so, and then the second one will be 5 digits, 5 zeros, and then a 2. And when we get to 10, there'll be 4 digits in front, and so forth. And it just lists nicer in your Finder windows that way. And then it'll be here. It'll have dat. So what this command does is it builds the string of characters and calls it file name. And that's really what this is. This is turning the number 0 into a string, number 2 string, and it says number 0, and use this format. This is basically a C code format. Use 6 decimal places to do that. I think it'll make more sense when you see this run. Okay, so we have the file name, and then we're going to dump, we're going to save, using an ASCII file, the variable S. And so I think that's pretty self-explanatory. So this writes the file here. Now we're in the main loop. I'm at the bottom of the code, so this is all there's left in the code. The main loop basically iterates on I step. That's the number we set at the top of the code. That was at 40. And then it's going to loop through, and it's going to calculate this nested do loop. J is going to go from 2 to 5, and I is going to go to 2 to 5. So 2 to 5, if you look back at our domain here, that's this point right here, 2 to 5, and then 2 to 5 and J would be up. So I'm just doing this interior part, right? So when you do central difference, you can't do all of the nodes. You don't want to recalculate the boundary nodes. They need to remain the boundary nodes, and you're just calculating the interior nodes. Well, again, the analogy that I like to use is it's like a musical instrument, this differential equation, right? The musical instrument itself, like a guitar, it could play whatever song you wanted, but you have to impose boundary conditions on the guitar and initial conditions. The boundary conditions are you have to put your finger somewhere on the string and confine the string, and then the initial condition is you pluck the string. And so then it plays that particular song or that particular piece of music. And the guitar could play any music given the right boundary and initial conditions, right? So that's what we're doing here. We're imposing initial and boundary conditions to get a specific solution. And we hope it's a specific solution, the one that we want. All right, so that's what we're doing here. We just calculated the nodes in front of the step. So that's why I call this in front of the step. And then this is the stencil right here. If we go back and I remind you what this is, it's this equation right here that we derived earlier. So it's using the information from j equals +1 and j equals -1. And so that's above and below the central node. And then I equals -1 and I equals +1. So to either side. Right? So it's pulling that information from its nearest neighbors divided by 4, because that's just the way the math worked out. And that's equal to the value of psi. So that's why we have this image here. And then when we need to do on the other side of the step, we need to do this portion of the computational domain. So that's what I'm doing here. I am calculating above this step. So I'm going, I is going 6 to 9, and j is going 5 to 4. And so I recalculate the stencil. Then I build the file name again. So I call it psi num to string, and in this case I'm using n, iteration number. So the file name will have embedded in it in the iteration number .dat. All right, and then I write that to file, and I write it as an ASCII file. And an ASCII file is a file that we can read, like Matlab could open or Notepad could open. I'm sure you've all tried to open a file in Notepad and you see all that stuff that doesn't look like English. That's because it's a binary file, or it's some sort of compressed file, or even an encrypted file. An ASCII file means that any code can read it. ASCII was the original standard for computers back in the day. So that's the ASCII standard, which is readable. So it writes the file and then it closes the loop. So there it is, right? So if I come over to Octave and I take a look at where I'm at and I type pwd, you might be like, hey, wait a minute, that's that Linux command we learned last time. That's right. Octave, Matlab, they basically are copying Linux. I mean, Linux was one of the original operating systems, so that's why it functions just like a terminal window. So you already know a lot of commands if you know Matlab for Linux. Okay, so we're in the right directory, and all I have to do is run this, PSI.m. Let me pull up this so you can see little forward-facing step, Octave, domain here. Here's where we're at. And when I hit this run command, I guess I am, yeah, you don't put the M on there, sorry. There, it ran it, and it generated all these .dat files. And you can see where the zero padding is nice, because they appear ordered to me here, right? That's why I put those 6 digits here. This is 6 zeros, 1, 2, 3, 4, 5, 6. And so that's it. And so that's our M file. And I think what I'll do is I'll get out of there. I think I'll wrap this one up here, and we'll have a look at the data and plot it next time. All right, we'll see you again.